Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. So this week we are starting a new chapter. We are starting to talk about bending. So in this case, we are going to continue to review different types of deformation. We have looked at the case of the deformation due to the axial load. We have seen the case of torsion when you have the twisting of a member. And so this week we are going to start talking about bending deformation. So by bending deformation, I mean that we are going to consider the cases where you have a beam that is initially straight and that will turn into a curve like this due to a bending deformation. So when you think about bending deformation, there is really two ways that you can induce a bending deformation in a beam. The first way is to apply a transverse load. So if you apply a transverse load like this, so if you have a beam like this, and for example, you apply a 3-point bending like this, so you have two shear load like this, and then one shear load like this. So in this case, those three shear loads are going to balance each other. The beam is going to be balanced, but because of the fact that those shear loads are not applied at the same position, this will tend to bend the beam, and the beam will turn into a curve like this. So this is the first case. This is a case where you have an actual loading that is applied that is orthogonal to the longitudinal axis of the beam. And another way to induce a bending deformation is to apply a moment. So in this case, we are not talking of the same kind of moments that we talked about in the torsion chapter. We are not talking about a torque. We are talking about a moment that is applied within the xy plane. So, for example, if this is the x and this is the y coordinates, in this case, the moment is within the xy plane, and this moment again is going to cause the beam to turn into a curve like this, to turn a beam that used to be a straight line into now a beam that has the shape of a curve. So just like in the case of the previous chapter, the first thing that we need to do is to find a way to define the internal loads that will be applied within the beam. So in this case, what we need to do is we need to find a way to convert what we know, and what we know are the external loads that are applied to this beam, the external moments or the external forces that are applied to this beam, and to convert this into the internal loads, to convert this into the forces that are applied within this beam. When you apply the method of section and when you cut the beam into two parts, the force applied by the right to the left part of the beam, this is what happened at the inside, in the inside of the beam. So this is the internal load. And if we want to be able to calculate the deformation of this beam and the stress that is acting within this beam, then we need to calculate first the internal loads. So as a summary of the previous episodes, so what we talked about first was the case of axial load deformation. That is to say, when you have a beam like this that is subjected to a normal load along its longitudinal axis that will cause the elongation of the beam. Then in this case, the quantity that we defined was the internal normal load. And in this case, in the case of the internal normal load, so you cut the beam into two parts, you use the method of section, and the positive sign convention that we used for the internal load P of x is that it's always pointing towards the outside. That's how we define the positive sign convention. We need to define a convention because, again, necessarily the load applied by the right to the left is going to be the same magnitude but opposite direction as the load applied by the left to the right. So necessarily one load will point towards the right, another load will point towards the left, depending on whether you isolate the left or the right part of the beam. So we need to decide what is a positive internal load and what is a negative internal load. And for consistency, the sign convention that we decide is that a positive internal load is a load that is going to cause an elongation rather than a shrinkage. So that's a load that is always pointing towards the outside. So that's the first case. That was the case of the axial load. Then we saw the case of torsion. So in this case, torsion, you have a beam like this, and it's subjected to a twist deformation like this, to some torques that are applied along the longitudinal axis that cause a twist deformation of the beam. And in this case, to characterize the internal actions that are undergone within the beam, what we defined was the internal torque. So in the case of the internal torque, what we do, in this case, we defined it as the torque that is applied either by the left to the right, or the torque applied by the right to the left. And in this case, the sign convention that we defined for the internal torque is that you put your thumb pointing towards the outside, and then the finger gives you the direction of the positive internal torque. So in this case, again, necessarily one of those two internal torque will have a positive projection and the other one will have a negative projection due to the principle of action-reaction. So now we are talking about the case of bending. So where you have a beam like this, and this beam can be potentially subjected to some shear forces, or can be also potentially subjected to some moments like this. So when you talk about the beam, so first, when you subject a beam subjected to bending, there is no change in the length of the beam. Bending is not going to change the length of the beam. It's just going to transform a straight line into a curve. So if there is no change in the length, it means that there is no elongation. And if there is no elongation, then it means that there will be no normal load. There will be no normal internal load. So we don't have to worry about this. The other thing is that bending is not going to cause the twisting of the beam. So if there's no twisting, then there's no internal torque. So we won't have to worry about an internal torque that is transmitted from the left to the right part of the beam. But bending, since you apply some external moments and some external shear forces, then you will have an internal moment and an internal shear force that can be applied within the beam. So in this case, the two quantities that we will define, the two types of internal actions that we will define within the beam are going to be first, so the internal moment. And so in this case, the internal moment will be defined as the moment applied by the left to the right or the right to the left. And we will also define the internal shear, which in this case will be also defined as the shear that is applied from the left to the right or the right to the left. And so the same thing, we will need to define some sign convention so that we can use a consistent definition to characterize what is a positive internal moment and what is a negative internal moment, what is a positive internal shear, what is a negative internal shear. And that's what we are going to do in the next section. So what we are going to do is to define the internal moment and the internal shear of a beam that is subjected to tension, subjected to bending, sorry, in the very same way that we define the internal load or the internal torque. So for this, we will consider a given beam like this that is along the longitudinal axis X. And every time you want to define an internal load, an internal moment, you need to use the method of section and to cut the beam in at a given position X, and to define the load that are applied from the left to the right or the right to the left. So if you cut the beam at a given X, then necessarily the left part acts as a fixed support for the right part and vice versa, which means that the left part or the right part will apply different types of loads to the other part due to the fact that those two parts are attached to each other. So in this case, we said that in the case of bending, the two types of forces that you will have will be, first, you will have a shear force that is transmitted by the left to the right. There will be no normal force because there is no elongation, but you will have a moment. So you will have a moment that is applied by the left to the right or the right to the left. So the positive sign convention that we will be using is that for the moment, we will always define as a positive internal moment a moment that is inducing a convex shape for the beam. So what is that? So we will define the moment to be positive if it's like this or like this. That's going to be the internal moment, which we are going to write m at x. That is going to be the positive sign convention. So what is this types of moment? This types of moment is a moment that if you have these types of internal moment, that's a moment that will induce a convex shape for the beam. That's a moment that will make a smiley face for the beam like this. So that's going to be the positive sign convention for the moment. That's the type of moment that will tend to transform the beam into a smiley face like this. So that's for the moment. Now for the shear, again, we need to define the internal shear as the shear force that is applied by the right to the left or the left to the right. We know due to the principle of action-reaction that those two forces will be same magnitude but different direction. One is going to be pointing up, one is going to be pointing down. So in this case, by convention, what we will be using is that the internal shear will be positive if it's going down when applied on the right surface, or going up when it's applied on the left surface. That is going to be the positive sign convention for the internal shear. So again, the internal shear, a positive internal shear, will be a type of internal shear that is causing these types of deformation. Just as a note here, the positive sign convention for the internal shear is actually the opposite as compared to the sign convention for the shear stress. So if you remember, for the shear stress, the sign convention that we define for the shear stress is as follows. If you isolate a small portion, a small infinitesimal volume of a given member, the positive sign convention for the shear stress that we defined is like this for the shear stress tau, which is the opposite as the sign convention for the internal load, the internal shear load, where in this case the shear force is defined, the internal shear is defined as being positive if it's going down on the right and up on the left. But in the case of the shear stress, it's exactly the opposite. It's defined as a positive shear stress if the shear stress is going up on the right and going down on the left. So, of course, it's a little bit unfortunate that those two sign conventions are opposite to each other. The reason we are still using those sign conventions is that those sign conventions are the ones that are the most commonly used. Those are the sign conventions that are used in the textbook and that are commonly used in this field. So there is one sign convention for the shear stress, and that's usually this one. And then you have the sign convention for the internal shear, which is also this one. And despite the fact that those two sign conventions are opposite to each other, those are still the ones that are commonly used. So in this case, one thing to remember is that if you have a positive internal shear, this is something that will result into a negative shear stress due to the fact that those two sign conventions are opposite to each other. So now that we have defined the internal moment and the internal shear, what we are going to see in this chapter is that there's different ways that you can calculate them. And calculating the internal moment and the internal shear will always be the first step of a bending problem, because you will need to calculate this internal shear and this internal moment to be able then to calculate the value of the deformation and the value of the stress that the beam is subjected to. So one first method that will always work is to use exactly the same method that we have been using so far, which is to use the method of section. So you cut the beam at a given position X, then you isolate either the left or you isolate the right. And based on this, by writing the fact that the left or the right has to be at equilibrium, then you can calculate the value of the internal moment or of the internal shear. So this method of section will always work. But in the case of the bending chapter, there are some other methods that you can use, which can typically be faster and more convenient than using the method of section. So that's what we are going to talk next. We are going to see an alternative method, which is the method of integration, the integration method, which can be used to derive more quickly the internal shear and the internal moment of a beam that is subjected to bending without having to use the method of sections.